Okay, today we're going to take a look at the R part in the CART, classification and regression trees. Everything that we did so far in this class, well, in machine learning piece of the class anyway, pretty much revolved around creating a predictive model when your target is categorical variable, right? We started with pretty much useless example of Titanic, and we tried to predict which passengers will die and which will survive, right? And then we got a more realistic example where we were trying to predict which bank customers will agree to the unsolicited loan offer and which will turn it down, right? And we built gain classification tree for that. But the algorithm that we used, which is called CART, stands for classification and regression tree. That means that we can actually use the same structure in order to predict a numerical target. Okay? So, ladies and gentlemen, let's take a look at new data set. Go to Scholar, okay? Just like this. And in the Scholar, I believe I posted in the data files, go to the data files, at the very end, I posted the file called Corolla CSV, as in Toyota Corolla, okay? The file contains, I believe, 1,000 records, about 1,000 different cars, and we're going to take a look at that. You know what to do with the file, right? You download it, and then you move it where? To the disk C, folder data, right? And by now you probably know how to do it, right? Download, go to downloads, cut the file, copy that into the folder. Okay, so go ahead and do that. And I'm going to fire up the RStudio. Okay. First of all, let's take a look at the data itself, at the file. Okay. So I'm going to create a new clean R script. All right. Did everybody download the file? What's the very first thing that we always do when we start analyzing the data? Read CSV, right? If you didn't bring the data into the memory, you can't do anything pretty much. Okay, so I'm going to call it Corolla, and that is a result of the read.csv, quote unquote. And the file is located in C, folder data, / Corolla.csv, right? And you need all components of this file name, including folder, subfolder, drive, and extension, right? In order for this thing to work. Okay, so let's read the file. And you should not see any red indications, right? Meaning that you did everything correctly. Well, let's take a look at the structure of my data. For that, I'm going to use the function str, right? Just like what we did before. Structure of the data Corolla. Bam. Okay, so this is it. And for some reason, okay, there it is. It doesn't show me all of the data, I believe. All right, let me do this. Okay, there it is. Okay, so my data for Corolla. First of all, how many observations? Tell me. 1,000. How many columns in my data? 10. Okay, so price, self-explanatory, right? These are all used cars. Okay. Price of the car in whatever, dollars, euros, right? Then next one is age. That's not years, that's months. Okay. How old is the car in terms of months? Then the next one we have mileage, right? How many miles are on the car? Fuel type. Fuel type, note that the fuel type is the categorical variable, right? There are 3 different fuel types, okay? It says factor with 3 levels. CNG is, should be called LNG. I was thinking yesterday of renaming this one. Liquefied natural gas, basically. CNG probably stands for compressed natural gas, okay? There are countries which use natural gas as the instead of like petroleum, right? And then diesel and just regular gas, what we use in the car, not the natural gas, not the gas, but the liquid gas, right? So 3 levels. So this is a categorical predictor, right? All of these things, age, price, and mileage, they're numerical. What else? We have horsepower, which is numerical, obviously, right? How many horses are under the hood? Then next one is color, okay? So there are 2 levels, 0 and 1. Metallic. The color can be metallic, this silver kind of color, right? In which case it's a 1. Or non-metallic, everything else, blue, white, what have you, black, non-metallic, right? So it's 0, 1. Then automatic, same thing, 0, 1. If the car is manual, stick shift, that's a 0. If it's a 1, that means it's an automatic transmission, right? Engine volume, okay, in terms of, I don't know, what are the units, cubic centimeters or something like that. That's probably too much for cubic centimeters. Number of doors, okay, cars can be 4 doors or 3 doors or sometimes 5 doors, right? And the last one is weight, probably in terms of pounds, okay? So, and let's say I want to develop a model that is trying to predict how much the car will be priced, the used car, right? Based on everything else. Mileage, age of the car, what type of fuel it's using, what the weight, weight, right? Can it be the factor? The heavier the car, the more expensive it is? I don't know, maybe. Okay, so what I'm going to do is build the same type of model as what we did for predicting the bank customers who will agree to the loan or disagree to the loan, or loan mover ownership. So basically decision tree, okay? And I'm going to use pretty much the same approach as what we did before. Okay, for simplicity, I'm not going to split into the training and validation set, so I'm going to use my old data set as what? Training, right? To train my model, okay? So this time around, my target, the price, is continuous variable, right? It's not 0, 1, yes, no, that we had before, who will survive and who will die, okay? As in case of Titanic, but it's a number, right? I'm trying to predict how many dollars and cents the car will cost on the market if I know everything about it. Mileage, weight, engine volume, whether it's manual or not, etc., etc. Okay, so because our target is numerical, how do we call such model? Regression, right? Remember, we had 2 types of predictive models, right? 2 types. If the target is categorical, we call it classification model, right? If the target is numerical, we call it regression. All right, so let's call this model Corolla price regression tree, okay? Corolla underscore price underscore regression underscore tree underscore model. It's going to be a really long name, which tells you precisely what it is, okay? I'm going to use the function same thing, okay? Because it's a CART algorithm, it can build either classification or regression model. So I'm going to use function rpart, but it doesn't seem to understand what I mean. Is there anything I should do before I call the function? I need to load the library, right? So before that, I have to say library rpart, okay? Load the library into the memory, so run this line, and then after that, I'm going to say rpart, okay? Again, same thing really. I'm sending the function 3 arguments. Argument number 1 is what is my target and what are the predictors. My target is what? What am I trying? Price, right? I'm trying to predict the price. So my target is price, tilde, and if I want all predictors, I just put dot, right? That's it. By the way, question, kind of related to your project that you're doing. If I want to remove a certain variable from my model, how do I do that? Subtract, right? So if I want, for example, to remove the car weight, this is how I do it, right? Dot minus the weight. Dot means all the variables minus this one, okay? So, just a hint, that's something that you could use probably in your project, if you don't want to use a certain continuous prediction. Wink, wink. Okay? Alright, next thing, so this is my model essentially, right? I specify the target and predictors. Then the next one is, I'm going to say which data to use. Well, this is Corolla data, right? All of it. And next one, method. When we wanted the model to be a classification tree, we said class, right? This one is not a classification tree, right? Because the target is numerical. I'm going to use ANOVA. Let me spell it right. ANOVA. Not Avona, but ANOVA. ANOVA, you learned about ANOVA in your statistics, right? Stands for analysis of variances. And that's essentially what it is. I'm going to explain to you how that works in just 1 second, okay? So, ANOVA. And let's go ahead and run the model, okay? You should see no red color. And after that, let's take a look at the results, right? So, I'm going to have to load the library. Which one? rpart.plot, right? So I want to see the tree and all of its glory. I want to load the visual library that draws the tree for me, right? So rpart.plot and my model, which is called Corolla _ price regression tree model. Bam. Okay, so I'm going to run this one. And there it is, okay? And you should see basically the same thing, right? Did everybody get the model? Yeah. What's not found? Corolla. That means that your problem is right here. Make sure that... Yep. Okay, so this is the tree. And how do you interpret the tree? It's pretty much the same way how you interpret the classification tree, okay? So let's look at this one, for example, the node which is on the far left. And again, we're looking at the terminal nodes, right? Because terminal nodes that do not split any further, they give you the final classification, well, not classification in this case, final answer, right? So, basically it says that if the age of the car is above 33 months, right, then we go to the left, and at the same time age of the car is greater than 53 months, then we go to the left again, then this node contains 50% of all data, right? Remember we discussed that earlier. How do you interpret all these percentages? If you add them together, that's everything. It should be 100%. So 50 plus 1 plus 30 plus 10 plus 8 plus 1 should be 100, right? So this node contains half of your data set, 500 cars essentially, okay? And this is the prediction. All these cars are predicted to cost $9,491, okay? So as long as the age of the car is more than 53 months, this is your prediction, okay? We predict that all such cars, regardless of anything else, right? It doesn't split on any other variable. Mileage does not seem to be important. Type of fuel, automatic versus manual, none of that seems to be important, right? All these cars will cost $94.91, okay? Now, do you see? Well, let's take a look at this one. Let's take a look at this one on the far right. Okay, what do we have? If the car is not older than 33 months, so it's 32 or less, right? And the next one, weight is under 1278 goes to the left, weight is greater than 1278 goes to the right, okay? And we're getting into this node, and it contains 1%. Do you see the same thing as what I see, 28E plus 3? What does that mean? Any ideas? 28,000, right? This is so-called scientific notations, right? So what are the scientific notations? Here, okay? Alright. So if we see something like that, 28E plus 3, E plus 3 means 10 to the power plus 3, right? So 28E plus 3 essentially is 28 times 10 to the power of 3, or in other words, 28,000, right? This is so-called scientific notations, right? Well, the only reason why R does it this way is, of course, to save space, right? To make sure, let's see, to make sure that we can fit, so it could fit number 9491 within this rectangle, right, in the leaf. That was just too long, so it replaced that with scientific notation, okay? In actuality, it's not 28,000. Let's actually do this. Something that we never did before, okay? This is a graphical representation of the tree, right? Kind of nice and very visual, okay? Let's just go ahead and do something that we probably should have done several classes ago. Let's just see what's inside the model, right? So I'm going to say, show me Corolla price regression tree model, just like that, okay? Without any rpart.plot, just show me what's inside this thing, okay? And this is the model, right here, okay? Believe it or not, it's the same thing as this tree, only not as beautiful, not as pretty, okay? Here on the top is your kind of legend, okay? How to interpret each line. Here's what each line contains. Node number, and then close parenthesis. How the split is done, the split condition. N stands for number of observations in this node, okay? Then deviance, well, it has to do with variance, basically, okay? The measure of variability, essentially, okay? And Y value, that's the value of your target dependent variable Y, okay? So, root says, root basically is this node on the top, right? That's the root. Contains 1,000 observations, correct? Then next one is deviance or variance, right? We're not really into, I mean, gigantic number, okay, so what? And the average among all 1,000 cars, so what each node reports is the average, okay? So 50% of the data ended up in this node right here, okay, on the far left, and the average between these numbers, that between these cars that ended up in this node, $94,091, okay? So for each terminal leaf, it calculates the average among all observations which are inside this node, okay? So average for all the cars, all 1,000 cars, is $11,860, okay? And that's what you see right here. But instead of 11,860, it told you 12e plus 3, right? You see that in the root node? So it rounded up essentially, okay? So it's not really 12,000, it's 11,860, okay? Similarly, this last node, okay, right here on the far right, which contains only 1%, right? So it's all the cars, that's our very last node. And the way how you know that this is a terminal node, you can see that star right here in my legend, right there, says stars, star denotes the terminal node. So I know that root is not terminal, I know the next one is not terminal, but this one is at the bottom, right? So the very last node at the bottom of the regression tree, okay, the split is based on the weight. Weight is greater than 1,277.5 pounds, okay? And that is correct because it says weight is less than 1278 goes to the left, but this is greater goes to the right, okay? It contains only 7 cars, okay? And according to my tree right here, okay, the flat tree, so to speak, the average price for all these 7 cars was, what, $27,523, right? That's the average, predicted average for all these cars. While here it's recorded as 28,000. Again, it's a scientific notation, okay? So just to save space, they're showing you things like that, okay? Yes, ma'am? Oh, yeah, there is actually. Let's see if it works, okay? You can turn scientific notations off. Let's see if it works, okay? So here's how to do it. I'm not sure that it is going to work for us, quite honestly, but let's see. The way how to get rid of the scientific notations and show the real number is to say options, and then after that we can go ahead and say sci-pen, scientific pen, I guess that's what it stands for, equals 999. So that's kind of a way to turn off the scientific notation and say, show me the actual number, okay? Not this E plus blah blah blah. Okay, so let's run this one, and let's rerun the rpart.plot line, right? And see if, yeah, it didn't have any effect, right? So it still says, yeah, I understand you want to turn it off, but hey, I don't have space for you, okay? So I'm going to keep showing you this awkward looking weird stuff, okay? But yeah, that's typically the way how to turn off the scientific notation. And you know what? It's going to be actually useful later when we're going to start doing the linear regression. In linear regression, they also, when you show the summary of the linear regression model, by default, R will show you scientific notation. But when you run this line, options sci-pen equals 999, it will show you the actual thing. Okay, so we will use that in the future. Okay, and that's essentially all I wanted to tell you about regression trees. Okay, so there is a way to use the same model, regression tree, when your target variable is numerical and not categorical. Regression tree, this is it pretty much. We're done with regression trees this semester, okay? So I'm not going to test you on regression tree in any form, shape, or way. I just want you to know that decision trees, generally speaking, can be of two flavors: classification, if your target is categorical, or regression if your target is numerical. It's a very popular data analytics tool, the classification tree, okay? Now let me tell you actually a little bit more about that. Couple of things. Well, first of all, why do you think classification trees, for example, can be popular? Is there any kind of business reason for that? Like, remember what we did on the test, which students will be dropping out of the university? It was a very clear set of rules, right? We ended up with like 3 sets of rules, and each one of them could be very clearly formulated, right? By looking at how the tree splits, right? So that's actually the reason why classification trees, or regression trees for that matter, decision trees, are so popular. Because they're very easy to interpret, okay? You can summarize them as the set of rules and give it to your manager, and so these are the people who will likely agree to the loan when you send them an invitation, okay? Very, very interpretable, okay? And they're easy to implement. Like, think of that, what's the next step, okay? I developed this model, like for example, with the bank, right? The model will tell me, based on historical data, right, which customers in the past most frequently agreed to the loan. What's my next step? What I can do basically is to take this model and implement it into the programming code, right? And put it on my server. And after that, next customer who comes in, are they going to agree to the loan or not agree to the loan? How do I know? Well, I just have to take their data and run through this model, right? And the model will spit out the answer, yay or nay. Simple as that, right? So essentially what I can do is, this procedure is called scoring, okay? I can take all of my current customers and score them against this model. And the model will tell me, that person likely not agree to the loan. That person is likely not. That person is likely not. But the next one is likely yes. Okay, so I can go through my customer list literally one by one and ask the model to give me a prediction. So whenever I see the prediction yes, that's my target population, right? I need to send to all these customers who are potentially yeses either a letter or the postcard telling them, hey, here is a new product that we have, this loan with really good interest rates that might be of interest for you, okay? So I can literally nail down my recommendations down to every individual customer. You see how cool that is actually? So I can implement that and, run it against my bank has 50,000 customers. Let's run 50,000 records through the model, and it will spit out 1,500 who are primarily yeses. Okay, that's the ones that I'm going to send the letter to. Okay, make sense? So really popular tool. Oh yeah, and another one, we're not going to discuss that in this class, just so that you know. Actually, even more popular tool, believe it or not, is something that's called random forest. Okay, very popular technique. Very similar to classification tree. Actually, it does use the classification tree, but here's the idea. Okay, it's something that's called wisdom of the crowd. Okay, the principle is called wisdom of the crowd. What random forest does is this: instead of building one big tree, just like this one, okay, I'm going to build a bunch of smaller trees. What do I mean by a bunch? 50, 100, 200 trees. Okay, so I'm going to pick some columns, not all of them, some columns, and some records. And I'm going to train a really small tree out of that small data set. Okay, what do I mean by small tree? It has only a handful of splits. Okay, 1, 2, 3, and that's it. Okay. So, I'm going to randomly pick bunch of random columns, bunch of random records, build a small tree. And another bunch of random columns, bunch of random records, build another tree. And I'm going to build, let's say, 200 trees, okay? Each one of them will have low accuracy, actually, okay? Because I'm using only small data set to train each of my trees. But I'm going to have 200 of them, okay? And after that, the reason why it's called random forest is I'm going to take each customer and run through 200 trees. So it's like a crowd of trees, right? And each tree votes. So I'm running a certain customer through 200 trees. Tree number 1 says no. Tree number 2 says no. Tree number 3 says yes. Number 4 says yes. Number 5 says yes. Okay? So out of 200 trees, let's say, for example, I don't know, 150 trees say that this is a good candidate for the loan. 50 trees say no. How do I decide, if you would have to guess? 150 say yes, 50 say no. Well, the majority, right? The majority of trees say yes. So I go with them. Okay. Amazingly enough, the resulting predictions are fairly accurate. The accuracy of the random forest oftentimes is higher than the accuracy of one big detailed tree. Okay. So each of these small trees is called weak learner because accuracy is not that high. They're weak. Okay. They don't predict things very accurately. They're wrong in a lot of cases. But because we have 200 or something like that trees, each voting yes or no, then it's kind of a synergy effect, okay? The majority of trees, that's the prediction that I'm making. Again, we're not going to do that in this class, but, well, the word of wisdom is on, in pretty much 100% of the cases, if you use the random forest model, bunch of weak learners, bunch of small, really shallow trees, the prediction is going to be more accurate than if you're using one big, very detailed tree, okay? But that's kind of beyond the scope of this class. Just wanted you to know that there is such model out there, okay? Yay? You're awfully quiet. Say meow. All right. Okay, well, ladies and gentlemen, today, the reason why I brought this up, this data set, Corolla, today we're going to start looking at a new topic, okay, which you actually learned already in introductory business statistics, so we're going to brush it up again, okay, so that you remember, and later we'll use that in a more advanced model, okay. This topic is called linear regression, and we're going to start with simple linear regression. I'm going to use the same data set, Corolla, okay. So the idea again is that I predict numerical target, which is the price, based on a whole bunch of predictors, right? That include mileage, age, type of fuel, automatic versus manual, metallic color and non-metallic color, number of doors, weight, engine volume, all that jazz, right? Okay, so linear regression is trying to build a model which looks like that, okay? Y equals, what's the equation of the straight line in the United States of America? mx plus b. mx plus b. Whoa. What do you call, oh god, mx plus b. What do you call m? That is the slope. What do you call b? intercept, or y-intercept sometimes called, right? Y-intercept. What do we call x? We call x, right? Well, not a multiplier. Well, obviously, m times x just means multiplier of m. Right? Now, independent variable. Independent variable. Or how did we call independent variables during the last 7 weeks? Starts with pre, ends with dictors, right? Predictors, right? Or predictors. Predictor. So this is one predictor, right? And how do we call y? If x is predictor, then y is starts with target, right? So this is target, okay? Target. This is my target. Or sometimes it's called dependent variable, right? Dependent variable. Why? Because it depends on x, okay? Variable. Okay, cool. All right, and that's what essentially I'm going to try to build, okay? The model that looks like this, but applied to Corolla prices, okay? So obviously, in my model, y is going to be price, right? Okay, well, let me ask you this question, ladies and gentlemen. Out of all of these, let me go back. Yeah, out of all of these predictors right here, okay? This is the bunch of my predictors, right? Which one, in your opinion, affects the car price the most? Probably mileage, right? It's the single most important thing that you need to know about the car, right? How extensively it has been used. So what's the general rule? Mileage goes up, price goes up, right? Oh, price goes down. Okay, got it. All right. So the higher the mileage, the lower the price. So I can expect, if I go back to my equation, right? Whoa. Come on. Okay. If I go back to my equation, then I guess what I'm looking for is this. M times my predictor, which is the mileage, right? If I want to build simplest model, okay? So we're starting with simple linear regression, okay? M times the mileage plus the B, right? The intercept. Okay, so this is called simple linear regression. Simple linear regression. Okay, why is it simple? Because I have only one predictor, okay? Of course, it's not the only thing that affects the mileage. The price, right? But it's probably the one that predicts the mileage the best, right? It's the strongest predictor, so to speak, okay? Other things affect the price as well, right? The engine volume, right? Because it drives the power of the car. Color probably affects. I know that transmission type, automatic versus manual, it does affect the price, right? And then a bunch of other things that are not even included, such as, for example, extra features, right? Sunroof, CD changer, I don't know, anti-locking brake system, leather seats, right? These extra features and, trims and stuff like that. But among all the predictors, probably mileage is the strongest predictor. So essentially, when I'm talking about training the model, simple linear regression, it boils down to two things, right? I want to know what the value of M is, the slope, and I want to know what the value of B is, the vertical intercept, right? Once I know both of these, M and B, well, that will give me a model, right? Then I can take any car with whatever mileage, plug that into the equation, and get the estimate of the price, right? What this car can be worth on the market. Okay, but let's go back to R, okay? Yeah, let's go back to R, okay. Before we proceed, before we actually build the model, let's kind of discuss things in general. True or false? If I plot price versus mileage, then it should look like low mileages give me high prices, high mileages give me low prices, right? There should be a pattern of sorts, right? Okay, let's try that. I believe we never did that in R. We did that in Tableau, that's for sure. How do I call the plot where I'm trying to represent two numerical variables? And they are numerical, right? Price is y, numerical, versus mileage is x, which is also numerical. Scatter plot, right? So let's do the scatter plot. Very simple. Okay, in R, and that apparently is the only thing that we're going to have time for today. Okay, so it's just simply plot, P-L-O-T, and once you type the plot, okay, let me go back. Okay, yeah, you see how do we call this thing that shows up and kind of tells you a short story about what you're trying to do? Tooltip, right? This tooltip tells me that the first thing that I have to send to the function is x, my horizontal dependent variable, right? Next thing is y, my vertical or dependent variable, okay? So x is what? What's my predictor? Mileage, right? And how do I address mileage? I have to say data name, $ mileage, right? Data name is Corolla, $ mileage, comma, and my y, same thing, right? Corolla, $ price. And that's pretty much enough by itself, right? I supplied the absolute minimum information. If you run this line, you will see that, okay? Now, does it look like low mileages imply high prices and higher mileages imply low prices? It does, right? Somewhat. It's not a perfect straight line, right? Because if I forget this point, this cloud of points right here, that kind of seems to be a little high, right, with low mileage, and concentrate on this cloud, that looks like a straight line to me, right? But in actuality, well, there is some sort of the curvature, right? So I can see that as the mileage is getting lower and lower and lower, the price climbs up, right? Up until about, I don't know, 40,000 miles. Then it kind of turns up a little bit, right? So it's not a perfect straight line type of pattern, right? But for the most part, it is straight line, okay? So I can certainly try and use my simple linear regression to make predictions, okay? But since we're out of time, let's do it. When's our next lecture class? It's going to be Friday, right? Okay, so we'll continue Friday. And I'll post the video.